This meeting is being recorded.
Okay, hello and welcome to the next meeting of New England Dynamics and Number Theory Seminar. This week we are on the West Coast, and our speaker is Srinivas from University of California, San Diego. And the talk is titled Random Walks on SL2FP cross SL2FP. Go ahead, Srinivas.
Thank you, Professor. So this talk is based on joint work of Professor Golsefidy and I. And the work in this talk has been published in two papers, one that got into JEMS and another generalization of that work that got into TAMS. So these papers are pretty good. I've already seen two good use cases. One good use case was by a work of Lior Silberman et al. And another one is coming up in, I think, a paper of Emmanuel Broyard. So this work has some good core, lets you boost your own work, basically. It's a good it's a good helper theorem. So let's see what it is. And I'll go over some background about how random walks in these finite groups of lead type usually work. And then I'll get to the result that we proved. So I know that I was talking to Tariq at a seminar in Berkeley in March, and the kind of math he does is, very far from the math that I do, although we both do dynamics. So that's why I'm just going to go over some background and the general flavor of the stuff. All right. So first of all, we're going to deal with finite groups and Cayley graphs of finite groups. So obviously with infinite groups, we have groups like the free group, whose graph kind of looks like a tree because there's no relations. Then you have amenable groups like Z, whose graph, or Z cross Z, whose graph looks like a grid because you have a lot of algebraic relations. So we kind of want to construct the analog of that in the finite setting. And in order to do that, we had to define what an expander graph is. Okay, so an expander graph is a graph with vertices V and edges E, such that if you have a subset of vertices, and then you look at all the edges or all the vertices connected to that subset, which are not in that subset, then it's a positive proportion of that subset. Basically, you expand. So for example, I'll draw a graph that is not expander, or rather has a very small um, um, expander constant. So if you take this dumbbell graph over here, and then this side has n vertices and this side has n vertices. Well, if we look at this set over here, this set of vertices, and call that A, then the boundary of A is actually just going to be this one vertex over here, because the boundary, partial A, is basically the set of vertices that are connected via edges to this set of vertices, but are not inside the set. So the boundary of this set A is going to have size 1. Therefore, this ratio of the boundary divided by the size of A is 1 over n. So basically, a set like this does not have good expansion properties. An expander graph is one where the boundary of A divided by A is always greater than some constant C as the size of this set goes towards infinity, or the size the graph goes towards infinity, if you wish. And basically, you want the size of A to be lesser than the number of vertices over 2, because if the size of A is bigger than the number of vertices over 2, like, this just won't hold. All right, so why do they matter? If the degree of the vertices are all lesser than k, and the uh, number and the degree is much smaller than the number of vertices, then these graphs are very sparse. That is, each um, vertex is not connected to too many neighbors. Okay, and if your expander constant is greater than 0, then these graphs are actually very well connected. The diameter of the graph is at most 2 times log the number of vertices divided by log 1 plus c. And so if you have graphs that are sparse and very well connected, then this is very good for computer science. And also, I forgot to mention there's a lot of applications towards number theory, and I'll mention them in the citations over here. Okay, so here's an example application of expander graphs. This is very computer sciencey, but basically the idea is that if you have a function that's either true or false, and the probability of that, and it's a random variable, and the probability of that being wrong is less than 1/3, you can use expander graphs in order to make this 1/3 as small as you want with using only d many computations more. So a lot of this can be found in expander graphs and their applications by Wigderson, Lineal, and Huri, which is a great survey. All right. So now it's let's get to the linear algebra, right? I can't remember who told me this, but I think it was someone at Ohio State when I was doing my undergrad. But all good math should boil down to linear algebra and combinatorics, right? I don't know. Maybe I'm wrong. But anyways, so if you have a k-regular graph with adjacency matrix A, so the adjacency matrix of a graph A is basically the following matrix. It is Aij equals 1 if the edge I comma j belongs to your edge set, or it's 0 if if the edge I comma j does not belong to your edge set. Okay, so if you have a k-regular graph with adjacency matrix A, then we can take the matrix 1 over ka, and this basically represents sort of like a random walk. Well, it's not really a random walk in this case because your A is arbitrary, but this will be a matrix that will represent a random walk in the future, and I'll get to that. So we note that the only one eigenvalue of this, the only one eigenvector of this matrix is going to be the eigenvector that is constant over all the vertices. So the reason is basically like the proof of the maximum principle from combinatorics. So if you consider the vertex v at which this function has largest magnitude, then that means you have a convex combination of neighbors. And I should have said, yeah, you can't have self loops, otherwise this might be false. But anyways, so you can't. No, actually, it's still true if you have self loops. But anyways, you have that this maximum value is a convex combination of its neighbors. So therefore, the neighbors also take on that maximum value. And then so you can have that process just spread. And then eventually, it's constant on connected components. So yes, I had to add connected over here. All right. So therefore, 1 sub v. 1 is the largest eigenvalue with unique eigenvector if G is connected. Okay. So now we can define lambda G. Lambda G is the second largest eigenvalue of 1 over Ka. Okay, so the second largest eigenvalue is very important to us. So some people call the second largest eigenvalue the spectral gap, and other people call 1 minus lambda G the spectral gap. So it's really up to you, but like, you know, when we're either trying to find an upper bound on this lambda or a lower bound on 1 minus lambda. So it can easily be inferred from the context. All right. Any questions? Sorry, I can't see the chat. None? All right.
It's okay. I'll watch for the chat just in case. I'll let you know if something happens.
Awesome. Thank you, Professor. Okay. So now for any graph, we can define this Cheeger constant over here, h of g. That is the minimum of the boundary divided by the number of vertices. Okay, so how does this, which we saw in our definition of expander, relate to the second highest eigenvalue. And then we realize the following, that this Cheeger constant over here, or rather, let's just say discrete Cheeger constant, is bounded above by this term over here, how far away the second largest eigenvalue is from 1. And it's bounded below, again, by the same term. So the lower bound is not too bad, like it's just applying the definition. And the upper bound is actually non-trivial. There are 4 great proofs found in a paper by Fan Chung called like 4 proofs of the discrete Cheeger inequality or something like that. And like one of the proofs actually goes through the PageRank algorithm used by Google. So that's interesting. Anyways, so we have, so every K-regular graph is obviously an HG K-expander graph, just by definition. The way we define this Cheeger constant term, every K-regular graph expands at that rate. So therefore, if we can somehow have an upper bound on this lambda of G, we basically have a control in both ways of this Cheeger constant, or basically telling us how quickly our Cayley graph expands.
So are these, how sharp are the estimates?
How sharp? Okay, so I think that this one is, I think this one is pretty sharp, and this one is not sharp, but state of the art. That's my belief. I haven't thought about this earlier, so if I had to shoot from the hip, that's my guess. But I believe that I don't recall this being sharp, but like it's obviously it's state of the art. All right. Yeah, sorry. Yeah, I'd had to know that better. All right. So given a group H and a generating set S, we define the Cayley graph for the purpose of this talk to basically be the vertices being H, that is, your vertices are elements of the group, and your edges are elements of the group connected with another element of the group, which is only one multiplication away, using the generating set and its inverse. Okay, so for example, let's look at some easy Cayley graphs. So if I look at the Cayley graph of Z mod n Z with the generating set plus or minus 1, then the Cayley graph looks like this. So you just start at 0, and then you can add 1 or subtract 1. When you're at 1, you can add 1 or subtract 1. Okay, so the Cayley graph is over here in this case is obviously not an expander, because basically if I pick any set like this, then it's only connected to 2 boundary vertices. Therefore, the Cheeger constant of this guy, of this graph, is always going to be greater than, I guess I can take the largest possible set would be something like n over 2. So 2 divided by n over 2. Okay, something like that. So therefore, these Cayley graphs, as n goes to infinity, their expansion constant goes towards 0. Okay. So I guess now the obvious question that's in our face is, can we find a sequence of groups and generators such that the size of these groups goes towards infinity, the size of the generators remains fixed, and the expansion constant is bounded below as the size of these groups go towards infinity? All right, so let's look at some examples. If G is any finite group and S is a uniform random subset of size log G, then we have that the that second highest eigenvalue is less than 1/2 with high probability, around 1 minus 1 over the size of the group. So this is a cool theorem. They use random matrix theory for this. This is pretty fun. Okay, then as mentioned earlier, if G is abelian, in this case, like this ring to the nth power, and then the size of the generating set is n, then we have that the second highest eigenvalue is cosine 1 over q to the n, which is approximately like 1 minus 1 over q squared to the n. So the second highest eigenvalue as q goes to infinity basically converges to 1. So these groups don't form a family of expanders. Okay, so now here's an interesting result. So using Selberg's result about the Selberg zeta function, we can actually say that if you pick these two generators of SL2 Z mod PZ, then we have that for all p greater than 0, that this eigenvalue is bounded above by some absolute constant, which is lesser than 1. Okay, so how to use Selberg's 316 theorem to get this result? It's in a blog of Terence Tao, but basically you suppose the opposite, and then you get a contradiction to the Laplacian, or the spectral gap of the Laplacian, being bounded below by 3/16. Okay. So let's define an expander family. We say that a family of graphs is an expander family of graphs if for all I inside the index set, Gi is a CK expander graph. Okay, so that makes sense, right? You have a family of graphs, and for every I inside the index set, these graphs are all expander graphs. So here's a cool theorem of Weiss and Lubotsky. It states the following, that if your groups, and if you have a family of groups and generating sets, then there exists an n such that for all I and I, and you have that the solvability index of those groups is lesser than n, where by solvability index I define the smallest number of commutators you have to take in order to get to the identity, then we have that the Cayley graphs are not an expander family for any c greater than 0. Okay, so here's the reason. The reason is that if you have a bounded solvability index, you have too many relations, right? And if you have too many relations, then you can't expand. Because, for example, let's look at the grid. The reason why the Cayley graph of z cross z with itself, with the generators 0, 1, and 1, 0, is a grid, is because there's too many relations, right? Like if you go to the right and go up 1, it's the same as going up and going to the right. So if there's too many relations, you're going to end up with something like a grid, and grids don't expand well. Whereas if you look at the Cayley graph of the free group on two generators with A and B as the generating set, then you're going to basically get this three regular tree on each node over here. And this expands great because there's no relations. If I go to the right and then go up 1, it's not the same as going up and then going to the right 1. So we can find analogs of this in finite groups. And basically this theorem is saying is that if you have a sequence of groups of bounded solvability index with a fixed number of generators, then you're going to end up with graphs which kind of look like this grid locally, and therefore it can't be an expander. All right. So now we get to Lubotsky's 1, 2, 3 problem. So in 1993, Alexander Lubotsky stated the following interesting problem. So let S sub L be these following generating sets of SL2 Z mod PZ. Okay, and obviously we want P greater than 3. So let P of L be the following predicate, that the Cayley graphs of SL2Z mod PZ with this generating set S sub L is an expander family. So basically, P of L is that following claim, except I plug in L into these matrices. So for example, P of 1 would be that if I pick the generating set to be 1, 0, 1, 1, 1, 0, 1, 1, and then like does the family SL2Z mod PZ with those generators form an expander family. And similarly, P of 2 would be just replacing L with 2. Okay. So now we note the following. S1 and S2, viewed as subsets of SL2Z, actually generate finite index subgroups of SL2Z. Therefore, using representation theory and Selberg's 316 theorem, we can say that P1 and P2 are actually true. So this comes from passing to the, what we love to call passing to the mother group, where all of these are quotients of SL2Z, and then P1 and P2 can be true by passing to the mother group. Okay, but S3 does not generate a finite index subgroup of SL2Z. S3 is a thin group, and it's actually a fun thing to prove. Can you prove that 1, 3, 0, 1, 1, 1, 0, 3, 1, that the group generated by this inside SL2Z is actually of infinite index? And it's really funny because the only difference is that 2 and 3, there's a huge difference between 2 and 3. I never really thought that 2 and 3 were that different until I worked this problem out. All right. So, okay, I believe that this quote, sorry, I should have replaced this with the verbatim quote from Gambourd's eulogy of Bourgain. Sorry, this is but this is a vestige of the old talk I gave. I should have replaced it with the verbatim quote. But so Gambourd and Bourgain were working on techniques for years on end, and they had in a seminar in Princeton at IAS. Luckily, their techniques actually merged like yin and yang, and then they solved the problem in like the span of a night. Okay, so here's the idea, and this is the Bourgain-Gambourd method. And especially for you, Tariq, since every time you go to a dynamics talk, dynamics conference these days, you're probably going to see this word. So this is for you. Consider the random variable x into SL2FP that takes values uniformly inside this generating set. Let xk be the product of k independent identical distributions of x. Then, if there exists an alpha beta such that if I let the random walk run for log p many steps, the probability of belonging to a subgroup is exponentially small in the index of that subgroup, then we must have that the Cayley graph is an expander. Okay, so this is basically the basic idea behind the Bourgain-Gambourd method. So why does this make sense? If you had that the Cayley graph was expander, you would definitely get this escaping condition over here. That is, if I run the random walk for log, and note that log p is on the order of the log of the size of the group. It's on the same order. So I guess I had to put a theta over there. So if I run this random walk for log the size of many group steps, then I would escape every subgroup with this exponentially small factor over here, which is 1 over the index of that subgroup to some power. So that's true if you had a spectral gap. The Bourgain-Gambourd method actually says the reverse, all right? So it says that if you actually escaped every subgroup with some probability, it doesn't matter what alpha and beta are, then I can actually take this result and reverse it and get that you actually have a spectral gap. So it's kind of like a reverse result. Okay. So is SL2FP special? After analyzing some group theory, we deduced that, okay, so now if we take this random variable x, which takes random variables inside, which takes uniform random values inside this set, then we note that x satisfies this property over here. With some fixed alpha and beta, and the alpha and beta do not depend on P. Therefore, we have that this generating set over here actually has a Cayley graph with a spectral gap. Okay, so that's the crux of the Bourgain-Gambourg method, is that combinatorial properties can be reversed to tell you things about spectral properties. Okay, so the above method depends heavily on two results. Well, one is of bounded generation by Helfgott. That is, if A is a subgroup of SL2FP that generates SL2FP and A has initial largeness, it's the size of the group to some delta, then I can take the product 1 over delta many times and get the group. Okay, so that was a cool paper by Helfgott. It solved a conjecture of Laszlo Babai. Okay, then also there's the quasi-randomness trick of Sarnak and Zhu, which states that every non-trivial representation of this finite group has to have dimension at least the size of the group to some power. Okay, so the above two items in group theory mean that your group is far, far away from being abelian. All right, if you have an abelian group, then obviously you have characters which are representations of dimension 1, which are extremely small. So it obviously contradicts number 2. And if you have an abelian group, you have arithmetic progressions, which means that this bounded generation result is false. So now we can kind of see like what the free group would look like if it was an increasing family of finite groups, right? It would look like SL2FP because it has these, and so we take properties of SL2FP to try and see what non-abelianness means in the finite setting. Okay. So here's the mantra of the Bourgain-Gambourg method, which has seemed to work across many different groups. It has worked for like Euclidean rotations like SO3. It has worked for SL2 p-adics. And the following month, and that's just because it works by additive combinatorics, which is very general. Okay, if X is a symmetric random variable into a sufficiently non-abelian group G, then the spectral gap of the Cayley graph only depends on the rate at which the random walk induced by X escapes subgroups. That is, the alpha and beta, such that for all subgroups, the probability after logarithmically many steps you're inside a group is the 1 over the index of the group to some power beta. So if you have this phenomenon, which we like to call the Diophantine property, if you have this phenomenon, you're done. Okay. Provided that you're in a sufficiently non-abelian group. All right. So this idea has been extremely productive and extremely lucrative. Let's go over some problems that are solved in dynamics and number theory. Okay. So first of all, you solve Alex Lubotsky's problem, 1, 2, 3 problem in this paper. All right. And in fact, like there was issues where people were considering like how thin a group is in order to talk about that eigenvalue. Well, this paper just blew through it. It doesn't matter how thin your group is. As long as you get that alpha and beta, you're good. Okay. Then after that, there's affine linear sieve expanders and some product. That's a paper related to number theory. On the spectral gap for finitely generated subgroups of SU2, like the same method, the Bourgain-Gambourg technique, but applied to SU2. Great paper. Then SUD, lots of non-trivialities in going from 2 to D. Then Bourgain and Varju, expansion SLD Z mod QZ, Q arbitrary. I really love this paper because this is one of my favorite groups. So same technique applied to this group, but you need a lot of new tricks. Then Golsefidy and Varju expansion perfect groups. So this deals with perfect groups, plugging in a finite field for P large enough. You need a lot of new tricks in this work too. The affine sieve relates the above work to number theory. Then they use the spectral gap to get a partial result. I don't know if it's the full or partial result in Zaremba's conjecture. And then finally, you can use these techniques when you take a perfect group and then you plug in the p-adics. Okay, so what is unknown is, can you take a perfect group and then plug in Z mod NZ and then try and prove that generators of this have a spectral gap using the above techniques? And my work with Professor Golsefidy is towards solving this problem. All right, so now we can finally get to the novel part of the talk. What is new? Okay, so we're going to use the Bourgain-Gambourg method in conjunction with an information theory inequality in order to solve a question of Lindenstrauss and Varju that we'll get to. But first, a little background. So we define, sorry, one sec, let me just, okay, cool. So we define SLNFP, semi-direct product FP to the n, as the following group. Okay, if you have a matrix and a vector and a matrix and a vector, the way you product it is you product the matrices, and then you take a matrix, multiply it by the vector, and then you add the other vector. All right, simple enough. So now we note that the map that takes a matrix and a vector to just the matrix is a homomorphism. That's because A, B here, A, B. All right. So now we note that if A is a subset such that the projection onto the matrices generates SLNFP, then either the group generated by A fixes a vector, or the group generated by A is the whole group. All right. So would you like, here's a little small proof of that fact. So suppose that A is a set which projects onto SLNFP. Okay, so now if A does not fix a vector, in FP to the n, then there's a vector of the form 0, comma v inside A times A inverse, where v is not 0. And now that you have a non-zero vector, and since you have every matrix, you note that A times 0, comma v, A inverse, this is going to be, sorry, there's no 0 in the matrices, this is I. So when you conjugate the identity, you're just going to keep the identity, but the cool thing over here is this vector gets perturbed, and then you're actually going to get the action of SLNFP acting on this vector over here. So now this orbit over here is very large, and therefore we actually know the following fact. We know that this orbit plus itself is actually equal to all the vectors. So therefore, I've shown you that if the projection of A onto the matrix component contains all matrices, then within 9 or 10 products, you can get the whole group. Okay. So therefore, given our mantra that algebraic properties should translate to these random walk properties, Varju and Lindenstrauss actually proved the following theorem as a toy project on a more difficult project. So they proved the following. that if you have this group of what do you call it, the affine group, and you have a generating set of this affine group over here, such that then we have the following, that the spectral gap of the generating set is actually bounded below by the spectral gap of the projection of that generating set onto the matrix component, and with a lot of fudge factor over here. So in the above, I told you that if your set projects down onto the matrix component fully, then you generate the group. So this is the quantitative version of that, saying that if you project your generating set down to the matrices and that generates the group quickly, then actually your original set generated the affine group quickly. So it's discussed in this slide. So the above result implies that if you have a family of groups with generating sets and these groups are the affine group, basically like SL and FP, semi-direct product FP to the N, then this is an expander family if and only if the projection, if and only if the matrix component with the projection of your generator set is an expander family. So the way they show this is by showing that if X is a uniform random variable into your generating set and V0 is a vector inside FP to the N, then they prove that the probability you fix a vector actually decreases exponentially in the number of steps you take in the random walk, right? So they basically say quantitatively that you cannot fix a vector. So the Bourgain-Gambord method over here says that we're done, because the Bourgain-Gambord method says that, okay, either you have to prove that you escape every subgroup, and then you can use that fact to with additive combinatorics to prove that you have an upper bound in the spectral gap. So why are we done over here if we know that we escaped the vectors? Well, we know that we escape subgroups of the algebraic of the matrix part just because we hypothesize that we have a spectral gap when we project this measure down onto the matrix part. And so all that's left for us to show is that we escape subgroups of this affine group which project down fully onto the matrix part. And as I showed above, that's basically those subgroups which fix a vector. Therefore, the probability of getting stuck inside a subgroup which fixes a vector decreases exponentially, and so you must have a spectral gap. Okay, so now you can have the next obvious question. So here is their open problem. They basically say that if you now take the product of two matrix groups, that is not just the semi-direct product of a matrix group with a vector space, if you take the product of two matrix groups, then should we have that the Cayley graphs of these groups with a generating set is an expander family if and only if the projection onto the left component is an expander family and the projection onto the right component is an expander family. All right, with the caveat that this generates the group, right? Because you could get stuck in the graph of a diagonal. Any question?
Maybe I missed it, but what do you assume about SP?
SP, okay. SP just generates HP cross HP over here.
So just any generating set?
Any generating set.
Okay.
Right. So if you have any generating set, they ask the following. And then I guess they also, they implicit in my definition of generating set, SP is bounded above by some K for all P inside primes. That's implicit in my definition of a generating set. That is, SP is this bounded size set such that the group generated by SP is the full product. And now you're asking this question where we have that the Cayley graphs of GP SP is an expander family if and only if the projection onto the left factor is an expander family and the projection onto the right factors expander families. Okay, so why does this problem make sense? Well, if A is a subset of GP such that the projection onto the left and the projection onto the right is HP, that is, it projects fully onto the left and fully onto the right, then either the subgroup generated by A is all of GP, or is the graph of an automorphism from HP to HP. All right, that makes sense, right? So if you take the diagonal group that's trapped inside HP cross HP, then this projects fully onto the left factor, projects fully onto the right factor, but obviously it does not generate the group. So, but if you know that you project fully onto the left and fully onto the right, and you generate the full group, then surely you must then you generate the full group. Okay, so what we do is we leverage the Bourgain-Gambord method, and now all we have to say is the probability of being trapped in the graph of an automorphism is exponentially small. All right, so here is our theorem. We basically say that the spectral gap of the Cayley graph, the product with this generating set, is bounded below by the spectral gap of the Cayley graph of the projection onto the left and the projection onto the right. So we answer their question, and yeah, here's the idea. So basically, we're going to define the Rényi entropy as the negative log of the L2 norm of the probability distribution. So let's take a few examples. So if your probability distribution mu is just given by like delta at the identity, then, and let's say x mu is the random variable that corresponds to this, then the Rényi entropy of x mu is going to be negative log of this guy squared, which is negative log of 1, which is 0. So the entropy of something that is supported on a small on one element is actually 0. And as you can guess, if mu is actually 1 over the size of the group and is a constant, then you can guess that the Rényi entropy of the random variable corresponding to the uniform distribution is going to be negative log the size of the group. Okay, so the Rényi entropy behaves like any entropy you would imagine, where the further spread out your probability measure is, the larger it gets. Sorry, this should be a plus log G. Yes, okay. So here's the special ingredient. Basically, let G be a finite group that acts on another finite group. Let X be a random variable into G and Y be a random variable into H. If X sub 1 and X sub 2, if X sub 1, X sub 2, Y sub 1, Y sub 2 are IID, then we have the following inequality. This is our new inequality. It basically says that the entropy of x1, y1 times x2, y2 inverse is greater than or equal to the entropy of x1, y1 times x1, y2 inverse. So, I mean, here's the key difference. The key difference is that we can replace this 2 over here with this 1 over here. So, all right, why does this matter? Well, let's see. So we note that every random variable into a product is basically a pair of random variables, that is the pair xl, xr. So let's write this inequality in the case where G is the group SL2FP cross SL2FP, which acts on HP by left and right multiplication. That is x, y acting on G is xgy inverse. Okay. So I'm just going to write it out by definition. So x1 acting on y1 would just be equal to xl1 times y1 times xr1 inverse. Okay. So now we have that. have written it out because we said that G acts on H by X comma Y acting on G is XGY inverse. Okay, so now we note the following is that there's this cancellation that goes on over here where it couldn't happen if this 2 and this 1 could not be changed to the same random variable. If this 1 and this 2 are different, then you can't cancel out, they can't cancel out each other, but when we expand this inequality, we see that they do cancel out each other. Okay, so I expanded this term to get this term, then I expanded this term to get this term. Okay, but now let me compute what's inside that term. So I get xl1 times y1 times xr1 inverse times xr1 times y2 inverse times xl1 inverse. Oh, so voila, these xr1s cancel each other out. So basically, we're left with the action of the left side of this probability distribution on this distribution over here. So we actually have a lot of information about the following random variable because in our hypothesis, we assume that the left side of the generating set has a spectral graph. So therefore, we can now exploit information about one side in order to talk about both sides. All right, and then we use this fact to prove that the probability of getting stuck in the automorphism of a graph is vanishingly small, which gives us the final result. Okay, so I think if there's any key takeaways from this talk, it's literally this inequality. It's extremely general. It works for compact groups. It works for finite groups. And yeah, I don't see why it wouldn't work for even like infinite groups. So if you have any questions about that inequality, please let me know. All right, so this has given us a lot of bounty. We basically got 2 great papers out of it. And basically, using analogs of the above inequality, along with other recent progress in the field by Tang and Zhang, who basically solved the conjecture of Professor Golsefidy about some product phenomenon over algebraic integers. We can basically try and get the super approximation conjecture for n and maybe every other ring. We're typing it up right now. It's a lot of technical work. Okay, so hopefully we should be able to finish typing up the furtherings of this idea by the end of the academic year. All right, that's all I had.
Okay, well, that's great. Let's give Srinivas, Srivatsa a round of applause, virtual or not. And any questions? Any comments? Yes. Yeah, I see that Tariq wrote a word of thanks in the chat. So Tariq, maybe you can say something to this effect.
Sorry, I said thank you and he kept calling on my name.
Oh, yeah. Thanks, Tariq. Yeah, so I think the key point is relating the action of it's so you have an action on the left and you have an action on the right, and then that acts on something in the middle by left times middle times right inverse. But you don't really know how the left and the right are correlated. So the inequality lets you decouple the left and the right. Yeah.
Okay. So just a general question. What do you think should come afterwards?
Okay, so what do I think should come afterwards? Well, we've kind of basically, okay, so we've pushed it to the limit for Z mod NZ. We actually have the theorem where if you take an algebraic group, plug in Z mod NZ, and then you take another algebraic group, plug in Z mod NZ, take the product of those. If you project onto the left and you project onto the right with the spectral gap, is it true that the whole thing has a spectral gap? Yeah, we have that theorem. So what is easy, like easy pickings is the same theorem in the Euclidean case. That is, if you have a measure on SO3 cross SO3, and then it projects onto the left with the spectral gap and a right with the spectral gap, does it have a spectral gap? The answer is probably yes, and should follow from literally a translation of the paper that we're going to put out this year. Like if you just translate every p-adic case to the Archimedean case, it should translate 1:1, hopefully. So there's that. There's also a semi-simple semi-direct product, a unipotent, which we're handling also, which we have done. So I think the future of the field is definitely the following question, and it's called Broyard's conjecture, where if you take a generating set of SL2 p-adics, can you prove, is it true that every single generating set of SL2 p-adics has a spectral gap? And that is unknown, actually. And the analog in the Archimedean case is called Sarnak's conjecture. Is it true that every generating set of SO3 generates the group, or SU2 generates the group with a spectral gap? So those two questions are unknown, and I think are the future of the field. Every or almost every. It's equivalent. If you can prove that, okay, so they're not equivalent, actually. So they're almost every would be new also. In fact, a positive measure of generators would actually be new, I think. So almost every would be new. Almost every would also be great. I don't know what exactly the conjecture is, every or almost every, but I'm sure if you proved either every or almost every, or showed it to Sarnak and Broyard, they would probably send you to the printing press, because those two would be like very, very good results.
Yeah, I think I've heard almost every, but
Yeah.
I don't know. I mean,
So here's something that's equivalent. If you can show that there exists a uniform spectral gap across almost every generating set, then you have shown it for every generating set. But if you can show spectral gaps but that are not uniform across generating sets, then yes, these are two separate problems. But if the universe works in a very beautiful way, then hopefully you can prove the following fact, that for almost every you have a uniform spectral gap. That's the big hope.
Just to make sure I understand correctly, so you're talking about the group SO3?
SU2, right?
Or SU2. So,
Yeah.
and by generating set, you mean the, say, a finite set whose such that the subgroup generated by it is dense in SU2?
Yes.
So it's kind of topologically generating.
Right.
Okay.
So yeah, you want to pick topological generators, and then you want to say that, okay, the spectral gap for all of these, for any topological generating set, is bounded above, is away from 1, and the only factor should be the size of the set you pick. So yeah,
okay.
I think that would be like the next big theorem, I think, and in this line, and it would be great because a theorem like that would actually say a lot about the number of solutions to words inside a group. It would say a lot about the derivatives of words. A theorem like that would have a lot of implications.
So can you remind me, there's also a somewhat related problem that might be of interest to people doing Diophantine approximation. If you want to approximate the identity with the products of generators of say in the ball of radius n, and then you say that say a pair of generators is Diophantine if you can do it with good if you cannot do it with a good speed.
Yes.
It is related to the spectral gap problem, right? At least in one direction.
Correct. Yes. So the Bourgain-Gambourd method actually states the following. So if you can sort of take SU2 and split it into different scales, look at it at different scales, that is, you discretize it and then you sort of look at it at different discretizations, where you take these discretizations to be smaller and larger. It states that if you have a Diophantine property at every scale, then actually you do have a spectral gap. And the vice versa is true. If you have a spectral gap, then you have the Diophantine property. So the Diophantine property is very important and is probably, well, I'm just spitballing here, is probably equivalent to actually having a spectral gap by the Bourgain-Gambourd method.
But
Right.
it's not proved to be equivalent.
So here's the I'm not very good with SU2 yet, but with SL2ZP, I can tell you for a fact that if you have a random walk such that the probability, so you can take a quotient onto SL2Z mod P to the KZ for every K, right?
Yes.
Right. So if you can say, now that gives you a random walk on SL2Z mod P to the KZ, right? For every K. If you have a random walk in the mother group, you project it down. So if you can say that you have the Diophantine property at every quotient with the same alpha and beta as in my slides, and then the only subgroup you care about is literally the identity, that is, the probability of hitting the identity is less than or equal to 1 over P to the K delta. And if this delta is uniform over all the Ks, then you have a spectral gap. And this is from the Bourgain-Gambourd method. So this is known.
Okay. Other
Yeah.
questions? Okay, well, let's thank the speaker again. This was great, and here's my button to stop the recording, and I'll see you guys some other time.
Okay, thank you.